Okay, we're finally in chapter 2, talking about matter and energy. What is matter? Matter is anything that occupies space and has mass. That's our definition for matter. So the 2 points, the 2 things that it needs to meet are that it occupies space, takes up space, and it has mass. Some types of matter are easily visible, like desks, people, the board. Other types of matter are impossible to see without magnification, like the air that's in between us. There's matter in the air. We just can't see it because it's really small. Then we also have this really corny shirt. You occupy space. You're sitting in a seat. You have mass, presumably, because I can see you. Therefore, you matter. It should be you are matter, of course, but it's not as cheesy that way. And you are important anyway. So there's that too. So matter may appear smooth and continuous. It often does. It sometimes doesn't. But it actually is not. If you were to zoom in closer and closer and closer to the surface of any bit of matter, it starts to look really freaky sometimes. But also you would find, if you continued zooming in until you couldn't zoom in anymore, you'd find that matter is composed of atoms. Atoms are the smallest little building block of matter, sort of in some contexts. These are submicroscopic particles, meaning they're smaller than you can see with a normal microscope. And there's about 100,000 of them across the width of an average human hair. So if you pull out a little piece of hair, or if you can imagine how thin a piece of hair is, fit 100,000 atoms across that, and that's the size of an atom. So they're really, really small. These are the fundamental building blocks of matter. So these, if you're familiar with Lego, I often say that these are like the 1x1 Lego brick of the universe. Everything's kind of built out of those, but unlike Lego, the 1x1s like stick together in different ways. So they're a little bit more interesting. Atoms can bond together to form molecules. And molecules are 2 or more atoms. The minimum is 2. And these are bonded together. Bonded or stuck together. And they have a particular geometric arrangement. So where they're positioned also matters. If you switch around the position, but it's the same units, that's a different molecule. So atoms make up the universe, and molecules made of atoms are like next block. All matter is made of atoms. These are some metal balloons, basically, that are sort of what we might expect atoms to look like in a metal. So we've got a bunch of these atoms sitting next to each other, and that's how they normally exist in metals. So in metals, they exist as independent particles. In other substances, they can bond together. Like we're seeing here, this is a representation of a molecule. I forget which one it is, but each of these spheres would be a different atom. So like we've got hydrogens here that are usually represented by the white balls, the white spheres. Our red spheres here would be our oxygen. The black spheres are going to be carbon. It's not important that you know all those details at this moment. I'm just letting you know in case you were curious. And then we also have nitrogen as the blue sphere. So each of the balls represents one of our atoms, and then they're connected with those, they're like the gray stick things. We'll get to play with these later in the semester. Those gray stick things are the bonds, the like sticky substance that holds them together. And we'll learn more about bonds later as we get into the class. So that's sort of what molecules look like. And if you were to rearrange, like if you were to pull this chunk off, this OH block off, and you were to like stick it onto the nitrogen instead, that would be a different molecule and it would behave differently. Or it might not exist. Like if you were to make it, it might just explode. Sometimes that happens. So those things, our atoms, our molecules, can be classified based on what kind of matter they are, what sort of state they're in. And we're probably familiar with the basic states of matter. So our lowest energy state is the solid state. And the solid state when we're writing chemical names out, is represented by a little s behind it. That's our lowest energy state. So lowest energy, and then we've got the L for liquid state, which is our next highest energy form, our middlest energy, if you will, our medium energy, if you won't. And then we also have our gas state, our gas phase, and this is our highest energy phase. And we'll learn some characteristics for each of those three phases of matter. So our solid state, our first lowest state of energy. In our solid state, our atoms or molecules, whatever our particles may be, are packed touchingly close to each other. They're close enough that they are interacting with their neighbors. There's no empty space between them and their neighbors. So two atoms, they're right next to each other. You wouldn't be able to squeeze another atom in between. You wouldn't be able to push them any closer because they're already as close as they can get. And in a solid, our neighboring atoms or molecules, so molecules that are just sitting, they're locked in, they may vibrate, they may oscillate, so they can do a little bit of kind of wiggling in their seat, but they're not getting up and moving around and swapping places with their neighbors. So they are stuck in their spot. So our solids have fixed volume. That's because of them being touchingly close. You can't squeeze them any closer to each other. And they also have a rigid shape because they are stuck in their spot. They can't move or swap places with their neighbors. And there are many, I'm sure, good analogies for what it's like to be in a solid state. Being in lecture is like being in the solid state if you're a student. If you're me, I can get up and move around as much as I want. But for you, most of you, you come in, you sit down in your seat, and you don't swap seats with your neighbors, just like in our solid. You're stuck in your spot. And you're not necessarily touchingly close, but we wouldn't be putting people in between the rows. Everyone's in their own seat. This is also similar to being at a movie theater. When you get to a movie theater, assuming that it's relatively full, everyone goes in and sits in their assigned seat. Maybe it's pre-assigned, or maybe you just figure out where you want to sit. Everyone sits down, the movie starts, and for the most part, people do a musical chair in the movie theater because that's considered bad etiquette. But that doesn't mean that you can't do anything, right? You can share a little bit of tea with your neighbor. You can say, oh, wow, look at them, on the screen, presumably. You can drink your popcorn, eat your snacks, all that sort of good stuff while you're at the movie theater. So this is sort of like being in the movie theater. In our solid state, we can also have different types of solids. So one type of solids is crystalline solids, anything that forms a crystal. So things like quartz. Quartz has a crystalline structure. That's why it makes the pretty repeating shapes that it has. It's shiny. Lots of other things can form crystalline solids, but the basis for crystalline is that there's long-range repeating order. So the way I talk about this normally is if we were to zoom in on one section, just really, really zoom in on one section of our solid, take a picture, and then pan over and look at a different section, would we be able to get those two images to overlap? If we could get them to overlap, then it's crystalline. It's got a repeating order. So if you're looking at one spot, you look at another spot, you might think, hey, that looks like the spot I was looking at before. That's our crystalline solids. So they've got a repeating structure. And oftentimes that structure is characteristic. So if you see a particular type of crystalline solid, thinking of like gemstones and stuff, they normally get cut specific ways because they look better that way. Or if you find crystalline structures out in nature, they'll often show up in the same sort of shape, like for quartz. We can also have molecules that are amorphous. They're more blobby. And they don't have a repeating structure or order. So silicon dioxide glass, which is a type of glass, is made up of silicon and dioxide, just like quartz is, but the glass doesn't have that repeating structure. So if you zoomed in, you took a picture, and then you panned over and you looked at another spot and you tried to compare those two images, you wouldn't get them to overlap. So there's not that long-range repeating structure. Different parts are going to look different, even though it's the same chemical structure. All right, liquid state. In our middleist energy state, our liquid state, the atoms and molecules are still close to each other. They're still what I call touchingly close. So you can't squeeze them any closer together. However, they're free to move around and past each other. So they can swap places with their neighbors. They can play musical chairs, and they do. So the liquids have the fixed volume because they are touchingly close. You can't squeeze them any closer together. But because they can swap with their neighbors, they don't hold to a strict, specific, rigid shape because they can sort of roll over their neighbors. And so this is why liquids will assume the shape of their container, because they can move past each other. They can flow. And this is sort of like people at the front of a concert. And I'm thinking of like a Billie Eilish concert, not like going to see our local symphony or philharmonic. People are probably not in the liquid state at those sort of concerts. So people at front of a concert. If you've never been to a concert, you've probably seen pictures of people or videos of people at a concert. Everyone up at the front, assuming that it's a big artist, right? There's tons of people crowded in, packed as close as they can be because they want to maybe reach out and get like a little finger brush from their favorite artist or whoever they're seeing, or they just want to get the perfect Instagram reel to share with their friends. Those people are packed in as tight as they possibly can be. If you, from the back of the audience, were to try to make your way to the front, you're probably not going to be able to squeeze between them. They are packed in as tight as they can be. But they can still move around each other. So if you've got a couple of people that know each other that are up in the front, they might maybe take turns. They might swap spots. Like, okay, well, you know, I got to be at the front for this song. Now it's your turn. Or if they have to go to the bathroom or something comes up, they could still make their way out because they can move past each other. They can swap places with their neighbors. But good luck getting back up to the front. So that's more like the liquid state. Liquid state is also more like us in the lab. We're at the maximum capacity of people in the lab, but we can move around and past each other, but we're not fitting any extra people in there. And then we've got our gas state. And in our gas state, this is our first and only state where our atoms and molecules are separated by large distances. So there is empty space between our particles, our atoms, or our molecules. And because there's empty space in between them, like we're seeing here, these red dots representing our atoms or our molecules, since there's empty space in there, we could push the lid of this piston down and compress those particles. We can get them to move closer to each other because there's empty space in between them. So gases are compressible. They are free to move relative to each other because they're not touching, so obviously they can move around and past each other. But because they are not in contact, they are compressible. Basically meaning that they can be squeezed. So if you think of a basketball that's not flat or not filled with water or sand, if you squeeze it, right, it gives a little bit, it'll compress a little bit, that's why it bounces. You can also do gas compression. If you take one of those $1 water bottles, the plastic ones, you drink all the water first because you're not going to be able to squeeze it if there's water in there. And then you twist the bottle. Most of us have maybe done this. You squeeze the bottle, twist it, and then it builds up pressure inside, and then you flick the cap off and it goes flying into the air. We'll talk about that again in like chapters. But gases are always going to assume the shape and the volume of their container. They're going to take up as much space as they possibly can. They're not going to all just lump to one side in the same way that solids and liquids do. The gas state is sort of what happens when we're done with class. So after we're done sitting in our solid state, I release you, you turn into a liquid state, and then we funnel out that door, and everyone goes their own separate ways in the gas state. We don't like walk out of the classroom or out of the lab in like a big amorphous clump, right, through the parking lot until we all climb into our clown car and then go home. We don't do that, right? We're in the gas state. We're all completely separated and we go our own individual ways. At least most of us do. So that's our solids, liquids, and gases, and it's all summarized in this table from our book that's very conveniently named 2.1.1.1 table. It's the first table in the first section, and it's the first of something else too, I'm sure. So different characteristics of our solids, liquids, and gases, if you want a review for that. Any questions about our states of matter? There are other states of matter, but those are the three that we care about. We don't really care about plasmas or non-Newtonian fluids or other things like that. So we can classify based on what type of phase it's in. We can also classify matter based on its composition, what sort of things are in it, or how many things are in it. So one of our things is a pure substance. Pure substances is just one type of atom or molecule. So it's just one thing the whole way through. That makes it a pure substance. It doesn't have anything else in there. And the other option is that you have more than one thing, so you'd have two or more things, and that would be a mixture. So 2+ types of atom/molecule, that makes a mixture. And you can have different proportions. You can have different ratios in mixtures. There's lots of different mixtures. Like if you just think about if you've had tea or lemonade, there's lots of different teas, there's lots of different lemonades. Some people brew up their tea really, really sweet. Some people drink it without sugar, right? So those would be different variable proportions in mixtures, being tea or other drinks. Even if it's the same things, you can make it up a different way. You can put in a different amount of the components. Okay, so we can classify everything that takes up space and has mass as matter. We can split our matter into pure substances, or we have just one thing. We can also have two or more things, and that's our mixture. And we can further break those down. So our pure substances can either be an element or a compound. We'll be talking about all these subdivisions later. We can also have homogeneous or heterogeneous for mixtures. So this might be a good review slide if you're trying to learn how we classify matter, and there's some examples in there as well. So our elements are a pure substance, so it's just one thing. And it can't be broken down into simpler substances. There's not a chemical transformation that you can do to break this down into simpler substances, sort of. All our known elements are listed on the periodic table. The one that we have in class is a little bit outdated, but there are 118 entries going all the way to what is labeled here as UUO, Ununoctium. That has a name now. It's oganesson. So some of those have been named since that periodic table was printed. So that's a pre-2019, I think, periodic table. I don't know what it's post. It might be like post-2000. But each and every one of those boxes is an element. So there's 118 options for elements. Some of those don't exist right now that we know of. So any of those boxes on our periodic table, those are our elements. Also, if you picked up one of these yellow sheets, which you should have, if you picked up one of these yellow sheets, you have a periodic table on here, and it's got the most up-to-date information for names on the periodic table. So you can see the OG down in there in the bottom right corner, our most recent element, our biggest element. We also then have compounds and mixtures. So if you don't have just one thing, or if you just have one thing but it's multiple things in there, that would be a compound. We're thinking of molecules here. So elements bonded together. So our compound is going to be a pure substance, but it's 2 or more elements. I don't know, I'm drawing the arrow there. But molecules fit into this classification. So molecules can be a pure substance. These are a lot more common than pure elements because there's 118 options on the periodic table, but you can mix and match those to make different molecules. So you can mix up like 2 carbons and 6 hydrogens, and that's a compound. You can mix up 3 carbons and 8 hydrogens, and that's a different compound. So you can make a lot of different options. You can cook up a lot of good stuff with those elements on the periodic table, making different elements and other compounds. They're not all molecules, but some of them are, many of them are. So these are a lot more common because there's a lot of options, and these can be decomposed into simpler substances. We can oftentimes break them into, any guesses? What would be simpler than a compound? Atoms. We can break them into atoms/elements. We take our little tiny hammer and we hit them until they break into pieces. More realistically, we probably heat them up or do something else like that to them. So that's our compounds. And then, so that's our other type of pure substances. We also have mixtures. A mixture is a mix. It's different substances, but they're not bonded together. They're just kind of, you threw them together, like you mix water and sugar to make sugar water. That would be an example of a mixture. The water and the sugar haven't chemically bonded. They're just kind of hanging out. They're associated with each other. And mixtures can also be separated. Some are easier to separate than others, and those proportions can vary. So for our mixtures, we've got some examples of mixtures. We've got, each of these is a beaker, and there's water in it. Our one on the left, we've got water with salt in it, and the one on the right, we've got sand. So these would be 2 different types of mixtures, and we'll talk about those here. So we can break down our mixtures based on how smoothly, evenly, uniformly they mix. A homogeneous mixture is going to have the same composition throughout. So a homogeneous mixture, every part is the same mixture, or every area is the same mixture. So thinking of things like lemonade, sodas, air, steel, and bronze are all homogeneous mixtures. If you take a sip of like a Pepsi or a cola, Coca-Cola, if you take a sip from one part of your drink and you take a sip from another part of your drink, they should taste the same because it's nice and evenly mixed. If it doesn't taste the same, you either have ice in there or something's wrong. So sodas would be examples of homogeneous mixtures. Every place that you were to sample from, you should get the same ratio of the components that are in there. A heterogeneous mixture, hetero meaning like other or different, these are non-uniform mixtures. So there's going to be different mixtures in different parts, different ratios in different parts. Or another way of putting it, not evenly, smoothly mixed. So marble, the stone that people like to make countertops out of that has those fun swirly patterns, those swirly patterns mean that it's not evenly mixed. If it was all the same consistency, all the same color, then that would be a homogeneous mixture, but it's got different patterns in it, so that's a heterogeneous mixture. Many types of soups and vinaigrette salad dressings, anything that you have to shake up before you use it, that would be a heterogeneous mixture. It's separated out. Like if you go and use some yellow mustard, because you're having a hot dog, and you don't shake it up first, and you just go, and it makes that horrible sound that it often makes. If you don't shake it up, there's a good chance that you're just spraying mustard water on your hot dog, and that's pretty gross. So you want to shake it up first so that you turn it from a heterogeneous mixture to a homogeneous mixture. Soups, similarly, if every single bite of your soup is the same, like let's think chicken noodle soup, right? We've got noodles, we've got chicken. Every spoonful should be slightly different. One spoonful, you're going to get a little bit of chicken. Another spoonful, maybe it's all noodles. If you're getting the same consistency, if you're blending your chicken noodle soup, something's wrong with you, probably. There's a valid reason for blending your soup, chicken noodle soup, but I can't think of one that I'm willing to share with you. So that's mixtures. Any questions about mixtures or pure substances? So again, for our pure substances, we've got elements. Any of the boxes on the periodic table, it's just one thing, and it's just one of our elements. So those are going to be typically atoms. We also had our compounds, so that's two or more things. Two or more of the things on the periodic table, those are bonded together, fixed, definite proportions. And then for our mixtures, we've got the smoothly mixed, the evenly mixed, homogeneous mixture. Same smooth consistency throughout. And we also had the heterogeneous mixtures that's going to be different in one part versus another. It might be clumpy, it might be lumpy, might have different colors and textures and consistencies in it. Okay, so thinking about these types of matter, let's identify these, if we can, as a compound, an element, a heterogeneous mixture, or a homogeneous mixture. Okay, first up, if we have a stuffed animal shark, is a stuffed animal shark going to be a pure substance or a mixture? It's going to be a mixture. There's multiple things in there. Is our stuffed animal shark going to be a heterogeneous mixture, meaning there's different consistencies, or is there going to be all one same material? What's inside stuffed animals? Stuffing. What's the outside of the animal made of? Not stuffing, right? So it's going to be different. Yeah, so this would be a heterogeneous mixture. Maybe a weird example of a heterogeneous mixture, but I like it. If it wasn't a heterogeneous mixture, then it would just be a blob of a mixture of the stuffing and the outside part, whatever you'd call that. I think skin is not the right thing to call that because that's wild. Okay, coffee. We're thinking of like the drink, the best part of waking up. Is that going to be a pure substance or a mixture? It's a mixture. And is it going to be a heterogeneous mixture or a homogeneous mixture? It better be a homogeneous mixture, unless you're making, I think it's often called cowboy coffee, where you've got the grounds in there. It better be a homogeneous mixture. Please do not have grounds in your coffee. It would also be a homogeneous mixture if you're getting a mixed drink from Dutch or wherever you like to go for your mixed drinks. If you've got sugar and cream and stuff in there too. What about alcohol in a thermometer? Is the alcohol in the thermometer, just the alcohol, is that, any guesses, a pure substance or a mixture? That is a pure substance. In thermometers, it's usually not a pure substance because they actually mix some coloring in there. But it is a pure substance. Is that alcohol going to be a compound or an element? It's going to be a compound. How do we know it's a compound? What's one way that we can guess that it's a compound? If we look at a periodic table of the elements, there's not a box for alcohol on here. So alcohol, it's not an element, but it is a pure substance. It's a compound. It's a mixture of elements. And then what about selenium? Is that a pure substance or a mixture? It is a pure substance. What kind of pure substance is it? Is it a compound or an element? It is an element. So selenium is on our periodic table. If you look in the upper right side of the periodic table, if you find the O, it's right underneath the O. It's the Se on the periodic table. Sorry, it's 2 under the O. It's the SE, not the S. Laser pointer. Hello. Selenium is an element. I'm just trying to see if my laser pointers, either of them will work. Maybe they were, oh, there we go. Selenium, Se on the periodic table. It's a real element. It does exist. I think it's like a trace micronutrient or something. So you probably get a little bit of it in your diet. You can buy supplements for selenium at the supplement store. Okay, so those are our 4 examples. We'll have other examples. These will also show up on exams. So this is just a little summary slide. We've gone through some summary stuff before, but you can come back to that if you need some summary. Okay, our matter, we also have different types of properties. So we've got 2 types of properties. We've got physical properties. We've got chemical properties. And these are distinct. These are different types of properties. Our physical properties, we can see, or that they can be displayed without changing its identity. So it's the same chemical or the same substance before and after. So this is going to include things like taste, smell, color, appearance, so like sort of the shape that it is, the melting point, the density, other things like that. Those are all going to be examples of physical properties. Like for gasoline, if you go to the gas store and you're buying some gas, putting it into your vehicle, and oops, you accidentally smelled a little bit of gas. Is the gas in your car still good? Yeah, it's still good. It still works. You don't like magically transform the gas in your car into some other thing by smelling it. The shirt today that I'm wearing is like kind of blue and white stripes. Are we all observing that? Is it still blue and white stripes after we've seen it? It sure is. The color, the appearance hasn't changed because we've observed it. Those are our physical properties. We also have chemical properties. And chemical properties are displayed by undergoing a change in identity. So it's a different chemical after it displays these chemical properties. For example, the flammability of gasoline. If you drive an internal combustion engine vehicle that runs on gasoline, or you're just having fun in the neighborhood with your gasoline, not recommended by the way, you burn your gasoline, and then after you burn it, is it still gasoline? No, it's not. It turns into something else. It turns into hopefully carbon dioxide and water. There's maybe some other stuff that's in there. But you can't just like route the exhaust from your car back into your gas tank and then like infinitely run your vehicle that way. There's not like some cool hack where you can do that. So in observing the flammability of the gasoline, or think of fireworks, once you've blown up a firework, you can't unblow it up. Well, you could, but generally you're not going to blow it up and then blow it up again, right? You only get one shot with your fireworks. Other things like corrosiveness, acidity, toxicity, these can also fall under the chemical properties realm. Okay, so going into some other physical properties. The atomic or molecular composition, so if you zoomed in all the way to see the atoms or the molecules, that composition, the things that are in the substance, doesn't change when the substance displays a physical property. An example would be melting, the opposite, freezing, boiling, condensing. All of those phase changes. Like if we take solid water and we heat it up and then it turns into liquid water. That melting point, the temperature that it changes, that is a physical property. It hasn't changed from being water to being something else. It was solid water and now it's liquid water. So observing the melting point doesn't change it. It's just a phase change. Chemical properties, on the other hand, like the flammability of candle wax and also the wick, but mostly the candle wax, that flammability is also a chemical property. In order for you to observe that a candle can burn, it has to burn And when you burn your candle, it goes away. It turns into other stuff. So it's no longer candle wax. Now it's hopefully just CO2 and H2O. But if we didn't do a good job of burning it, then there's maybe some carcinogens in there too. Fun stuff. Okay, some physical and chemical properties. Let's see how well we absorb that information. We've got the explosiveness of hydrogen gas. So hydrogen gas is explosive. Is that going to be a physical property or a chemical property? Does it change or is it the same thing? Yeah, it's going to be a chemical property. In order for you to blow up the hydrogen gas, like in the Hindenburg, it has to turn into something else. You can't double burn it. You can't double explode it. So that's explosiveness. And what about the bronze color of copper or the copper color of copper? Yeah, that's going to be a physical property. Observing that copper is the color that copper is doesn't change it to something else. So color, physical property. What about the shiny appearance of polished silver? Also physical. Appearance. Yeah, appearance is physical. It doesn't change just because you observed it. So the shiny appearance, also a physical property. It doesn't have to change into something else for you to see it be shiny. And then dry ice, which is ice but made from carbon dioxide, can sublime. It changes directly from a solid to a vapor. There's no liquid phase involved. So that sublimation process, is that a physical property or a chemical property? Is it carbon dioxide before and after, or does it change into something else? It's the same thing. Yeah, it's just changing from a solid to a gas. So this one is also a physical property. Because subliming is a phase change. Phase changes are always going to be related to physical properties. So moving from properties changes, we also have physical and chemical changes, which are related to physical and chemical properties. So our physical changes, we get a change in appearance, but not its composition. So similar to our physical properties, same chemical before and after. Like if you melt solid water into liquid water, if you boil it to gas water, it's all water all the way through. So this is going to include all phase changes. Every single possible phase change is a physical change. You're changing from the solid state where they're all touchingly close, they're not moving past their neighbor. You heat it up a little bit, now they can move past their neighbor, but they're still touchingly close. You heat them up some more and they're completely separated from their neighbor. The whole time, the chemicals, the atoms, the molecules, whatever they are the same, just arranged differently. In chemical changes, the matter does change its composition. So things like copper turning green when you expose it to air or to seawater, that is a chemical change because it's formed new compounds. It's a copper oxide that it's formed. I think we've got some more examples of these. Yeah, we'll go into more detail on these, but things like a color change that we're observing with this copper example, like the Statue of Liberty, used to be bronze colored, but it's been out at sea long enough. Somebody left it outside, and now it's all green. So don't leave your Statue of Liberty outside if you don't want it to turn green. It's my word of advice. Okay, so physical changes, state changes, phase changes are always phase changes or state changes are always physical changes. So changing from a solid to a liquid, liquid to a gas, gas to a solid, solid to a gas. Stuff like that. Always physical changes. Any physical change is just going to result in a different form of the same substance. So like smashing something, just like physically deforming it, like the thing that people used to do where you'd put a penny, RIP pennies, on a railroad track and then the like train runs it over and it smashes, or like the little things like at zoos and museums where you spin the handle and it smashes the penny flat. Those sort of things, it's still the same material that you put in, it's just rearranged and it maybe has somebody's face on it now, a different person's face on it now. Chemical changes, on the other hand, we are changing to new chemicals. So chemical changes result in new substances, or different substances at least. And this happens when we go through chemical reactions, which we'll, surprise, surprise, talk about a lot in this class. So anytime that a chemical reaction happens, we're doing a chemical change. Our chemical reactions generally have this form. Our chemical equations are going to have this basic form. We'll have things on the left, which I'll often call the left side or the reactant side. So our reactants are the things that are on the left. And what do the reactants do? Any guesses? They react and they produce something. What do they produce? They produce products. Yeah, so our reactants react and they produce products, and the products get shown on the right side. And in this class, fortunately for us, we aren't going to get too caught up on what's happening when in this chemical change, in this arrow. We're just going to say a change happens. If you go on and you take organic chemistry, then you'll be very curious about what happens during these arrow steps, but we're not going to focus on that, that's great news for all of us. We love that. You probably won't blow stuff up. Hopefully, in organic chemistry, most labs don't have stuff that blows up, ideally. It's possible that you'll run into like some potentially explosive chemicals, but there will be warnings about like, hey, don't let this explode. Like I took an advanced inorganic class in undergrad, and one of the warnings in the procedure, I think it was advanced inorganic, one of the warnings was, hey, during one of these steps, you create a contact explosive, so if it dries and you hit it hard enough, if you just like touch it hard enough, it explodes. So just be careful that you don't let your product or your intermediate dry. So that was exciting. Nobody had a thing blow up, but it was thrilling to know that we could just accidentally poof in our fume hood. Waste 8 hours of our lives. Okay, so this is our basic form for a chemical reaction. We can have multiple reactants, we can have multiple products. Sometimes we can even have double-headed arrows, so it can go both ways sometimes. Some examples of physical changes are changing between states of matter. That's our third time mentioning it. That's crazy how it came up 3 times. I wonder if it's important. We can also have separation of a mixture, like separating sand and water. There's still sand and water after you've separated them. If you like sift your soup, or if you like drain your pasta, you rinse your rice. Those would still be physical changes. We haven't changed the thing that we're dealing with. Physical deformations, cutting, denting, stretching, like with pennies or pieces of metal, those would also be examples of physical changes. And solutions not being like I've solved something necessarily, but where you're mixing a couple of things together in a liquid form. So like mixing sugar into water would be an example of a physical change. But some compounds, like table salt, particular types of compounds, this is an ionic compound, we'll learn about those later. Ionic compounds, when they dissolve, are actually broken apart when they dissolve, and that makes it a chemical change. So that's one weird caveat, where you would expect, okay, I put salt into water, the salt is now just in the water, but in the water it's different from when it was out of the water, when it was just the salt by itself. So that's one weird caveat. I include that specifically because where I used to work, we did a lab where one of the questions was asking about table salt dissolving in water, and is that a chemical or physical change, and everyone got it wrong every single time. So I included it in my slides. I don't remember if we have that here. Some signs of chemical changes include things like temperature changes. Temperature changes can indicate chemical changes. Light being produced like glow sticks, also a chemical change. Color changes can also be examples of chemical changes. If there's bubbles or gas that's formed, but not from boiling, it's like the baking soda and vinegar volcanoes that people do, the paper mache, and then the volcano explodes. Those would be examples of some signs of chemical changes. If there's a change in smell or taste, so if it smells like one thing and then you do something and then it smells like a different thing, like if you cook food, before you cook the food, like if we'll just use meat as an example, before you cook the meat, it has that real meaty smell. After you cook it, it's got that delicious meaty smell, the different meaty smell. So that would be an example of a change in smell, and it also probably tastes a lot different too. If it didn't, you did something wrong. Solids that forming solids from mixing two clear liquids can also be examples of chemical changes. So lots of examples of chemical changes, but the general idea is that we're making something new or we're making something different as a result. All right, I got distracted by my own thoughts. Some questions to test and see if we understand our physical and chemical changes. We've got boiling water. If you boil water, is that a physical or a chemical change? It's a physical change. Why? It's still water. It's just a phase change. So that would be a physical change. What about a nail, like the ones that you use for construction? Metal nail rusting. That one is going to be chemical. How can we know that it's a chemical change? What's one sign?
The oxygen is like oxidized.
It's oxidized. We can't tell that just by looking at it necessarily. It changes color. Rust is normally a different color than the nail. So that change in color is one clue that it's a chemical change. Let's say that we have a green solution, so like a green drink, and we've got a colorless drink, colorless solution. We mix those together, and we get a solution that's a pale green color. Do you think that's physical or chemical? I would say, yeah, probably physical. All we've done is diluted our green solution. This would be like if you mixed Mountain Dew Baja Blast with Sprite for some reason. Why would you corrupt Baja Blast like that? I don't know. But if you did that, right, you mix them together, you haven't changed it into some magic new drink. You haven't made something incredible and new. You've just mixed the two things together, and it's pale green because you diluted the green color. Let's say that we mix two colorless solutions. The resulting mixture has a yellow solid, a yellow precipitate that forms. So there's now yellow dust at the bottom of our solution. Chemical. Why is it chemical? There's a change in color. Phase changes are always physical. Solid formed from two liquids. That's a specific type of reaction that we'll learn about later. And this is actually even referencing a specific reaction that we'll also see pictures of later. Any questions about any of all this so far? We're cruising, we're having fun with definitions. Don't worry, we'll get to the math later. More math later. Okay, separating mixtures. You can separate mixtures. One way that you can separate mixtures through physical changes is by distillation. So distillation, or running a still, one of the ways that people have purified alcohol in the past. It's often illegal, but you can. So one way that you might do that is you would have a distilling flask. So you've got a mixture in this flask here on the left that we want to separate out. In this case, it's just seawater, or salt water. In other cases, we might have like orange peel that we picked, and we want to get the essential oils out. So we take a bunch of orange peel, we put it in there, we add some water, and then we heat this up. In this case, we're heating it with a Bunsen burner because it's just salt water, it's not going to burn. We've got a temperature, like a thermometer up at the top. You would use a thermometer up here, especially if you care about making sure that it doesn't get too hot. So some of the things will evaporate, but if it gets too hot, then more things will evaporate, and you might just send everything over. In this case, since it's salt water, it probably doesn't matter. We just heat it up, and the water evaporates, and then it goes down into this condenser, and it runs through this condenser tube, and in this condenser tube, we put cold water in the bottom, and then warm water comes out the top, or warmer water comes out. And basically, this is making a condensation zone. So it's cold water glass. You can sort of think of the water that forms on the side of a cold glass of water, like droplets. That's essentially what we're doing here, but we're constantly replacing the cool water to take out the heat. So our water that came into this condenser, this condensing arm, then turns into a liquid, and it drips down into the receiving flask here at the bottom. And so in this case, hopefully we're collecting pure water, none of the salt or other dissolved things are making it their way over. This is the way that a lot of essential oils are distilled or produced. They take stuff, you put it in a flask, you heat it up, the essential oils travel over, and you can collect them in the flask here at the end. So that's something, if you've got the glassware, there's other ways you can do it as well. If you've got the glassware, you can make essential oils at home. So that's kind of fun. You can also, distill alcohol that way, but probably illegal. You can also separate things through physical changes by filtration. So using a filter, so in this case we've got a ring stand and we've got a funnel sitting in our ring stand, and inside of that funnel, that's the wrong color to do that. Inside of the funnel there's a little piece of filter paper that we've sort of smashed in there. And that filter paper covers the whole area. So if the water or a slurry or a mixture in this Erlenmeyer flask wants to go through, it has to go through the filter. There's no way around it. And so all of the liquid will hopefully go through and collect in the bottom, and the solid, whatever this black solid is in here, will get caught on the filter and stay behind. So liquid goes through, and solids get caught, or are caught on the filter. This is sort of analogous to making pour-over coffee. It's not exactly the same, though. It's more like a French press, a weird way to do a French press. All right. Matter, I think we've talked about this. Matter is neither created nor destroyed. This is the conservation of mass, the law of conservation of mass. Box some things in for you. Matter is neither created nor destroyed in a chemical reaction. In a nuclear reaction, you can have significant, meaning like measurable changes in mass can occur. We will not be doing any nuclear reactions in lab. So we are not going to be observing any changes in mass. There are still going to be some changes in mass, but they're so small that we are not going to be able to detect them. We're just going to assume that they don't exist. So during any physical or chemical change, not nuclear reactions, but anything else, the total amount of matter remains constant. All that we're doing is rearranging our elements, our atoms, our molecules. We're breaking them apart and forming them into something new. We're not getting rid of any of the pieces or bringing in new pieces. Mass is conserved. Let's say that this slide is accurate, which it's not. All right, one sec. One of these days I'm going to fix it. Let's say we burn 32 grams of methane. Methane has the chemical formula CH4, so there's 1 carbon, 4 hydrogens. We burn that on our gas stove or with our gas stove. It will react with 128 grams consists of oxygen, which has the formula O2. So our reactants, the methane's one of our reactants, that's CH4. We also have the reactant oxygen. These react together to form, and to form here indicates our arrow. So this forms 88 grams of carbon dioxide and 72 grams of water. We'll just make both those pink. So this left side, these are our reactants. They react, they combine together, and it forms our products, in this case CO2, carbon dioxide, and water. And the amount of methane and oxygen that we had before, we measured them out in grams. That's a measurement of the amount of mass or matter that's in them. We had a total of 160 grams before. Afterwards, we had 88 grams of CO2, 72 grams of H2O. You add those together, and it's also 160 grams. So before, on the left, we had 160 grams, and after, we also had 160 grams because of the law of conservation of mass. We could also do a different version of this. So potassium hydroxide, which is shortened to KOH, readily reacts with carbon dioxide, CO2, to produce potassium carbonate, this formula, and water, H2O. So this is telling us what our reaction is. So we can set up a reaction. What's one of our reactants? Potassium hydroxide is one of our reactants. I'm going to write that in as KOH because it's shorter. What's our other reactant? Carbon dioxide, which is CO2. Do we have any other reactants? No, we don't, because we've got these keywords, to produce, and that's our signal that it's time to draw in our arrow, our reaction arrow. And then we've got some products. What is one of our products? Potassium carbonate, that's our K2CO3. And what's our other product? Water, which is H2O. And then we're told how many grams of potassium carbonate are produced if this many grams of KOH reacts with this many grams of CO2. The reaction also produces 36 grams of water. What's some information that we're given? .36 grams of water. Okay, so let's write that in under our H2O, because that's water. So 36 grams of water. What's some other information that we're given? Yeah, 88.0 grams of CO2. So we can write that in under our CO2. That's the amount of mass of CO2 that we have. What's another piece of information we're given? Yeah, we're told 224.4 grams of KOH. So you can write that in under the KOH. And what are we being asked to find? Yeah, we're being asked to find grams of potassium carbonate. One of the ways that we know that we're being asked to find grams of potassium carbonate is, well, it shows up right next to our question words, how many. So how many grams of potassium carbonate? So that's what we're looking for. Potassium carbonate is this K2CO3. How can we figure out how much K2CO3 was produced in this reaction?
We can add the KOH and the CO2 grams to see what our total grams are.
Yeah, so we know that mass is conserved. So we know the law of conservation of mass. The amount of mass that we have before is going to be the same as the amount of mass that we have afterwards. So if we add up the amount of mass that we had before for our reactants, it should equal the same amount of mass as we have at the end. So we can turn this into an algebra problem. Let's make what we're looking for x. The amount of matter that we have before equals the amount of matter after. So this 224.4 plus 88 is going to be the amount that we're looking for, and 36 grams of water. So we'll add in some pluses. We'll get something that looks like this. So we can add up the left side. We get 312.4 with what units? Grams. And that's equal to x, what we're looking for, plus 36.0 grams. To find x, what do we need to do? Yeah, we need to move the grams. We need to move our 36 grams to the other side, and we can do that by subtracting it from both sides. So minus 36 grams from both sides. That causes it to get canceled out on the right, and then we can plug that left side into our calculator. We get 276.4 grams equals x. So our answer is that this reaction produces 276.4 grams potassium carbonate. I was thinking about significant figures. Was anyone else thinking about significant figures? Cool. A couple people were thinking about significant figures. We don't want to forget, we do care about significant figures. It's important. Fortunately for us, in this problem, we're doing addition, we're doing a little bit of subtraction. What do we care about for addition and subtraction? Decimal places. And notice that all these numbers have one decimal place. So the least amount of decimal places is 1. So our answer should have one decimal place, and it has that. So we're good. We didn't miss anything. Yeah, if it wasn't that it worked out to be one decimal place for all of them, then we would have to backtrack a little bit and take a look at it. We didn't have to do that in this case because I set it up that way. W, professor. Questions about that example? Cool. We might see one of those on our first exam. Smiling. All right, density. We did it. We got to density. We're doing density today, density lab, I believe. The density of a substance is the ratio of mass to volume. So density has this formula. Density equals mass over volume, or if we shorten it, D equals M over V. Mass is usually in grams, often in grams, and volume is often in milliliters. Sometimes if you look it up on the internet, it'll give you like kilograms per cubic meter, which is a little bit annoying just because it's different units. But we can work those out if we really want to. But a lot of the time you'll see them measured in grams per milliliter or grams per cubic centimeter. Density is a fundamental property of substances. Different substances have different density, and if you change the size of an object, it doesn't change its density. A small hunk of copper, or a small piece of copper, has the same density as 5,000 tons of copper. Just as an example. And we'll be weird and add the E in there. Pretend like we're British. So the amount doesn't matter. If you've got a small amount, it's going to be the same density as a big amount. That's because both mass and volume change when you're scaling it up to the bigger amount. So that 5,000 tons of copper will also have a much larger volume, and it'll work out to have the same density. We can do calculations with density. So we can calculate the density of a substance by using that formula being D equals M over V. For example, a sample of liquid has a volume of 22.5 milliliters and a mass of 27.2 grams. We want to calculate the density. For some problems, it's helpful. You can always do this if you want to. It's helpful to write out our variables. This is, I think, more of a physics trick, more of a helpful thing in physics, but we can also do it in this class, and we'll do it again several chapters from now. So our volume 22.5 milliliters. Our mass is 27.2 grams, and we want to calculate our density. We know that density equals mass over volume. If we want to find density, we need mass and volume. We have mass and volume, and so we can just plug those in. So we're going to take our 27.2 grams. We're going to divide it by our 22.5 milliliters. We're going to get out some number. How many significant figures should our answer have? 3. So we are doing division. So we care about significant figures. Our top number has 3 non-zero numbers, so 3 significant figures. Our bottom number also has 3 significant figures, 3 non-zero numbers. So our answer should be rounded to 3 significant figures. The number that we get out of our calculator is 1.20, and then there's a whole lot of 8s and it ends in a 9, so that leads me to believe that that 8 probably just keeps going. And we can represent that by putting a bar over the top of it. So that's the number that we get out of the calculator. We'll, of course, round that. But first, what are our units? Our units, we just combined the units that we have. Nothing canceled, nothing went away. We didn't do anything fun like that. So it's just grams over milliliters. The units just come through the same way that they were in the reaction or in the equation. So our units are grams per milliliter. And then around this for 3 sig figs, we count over from the left. The 1, the 2, and then the 0 is our third. We look at the 8 to see how we round. 8 is bigger than 5, and so we round up. So it's 1.21 with units of grams per milliliter. Questions on calculating density? Cool, pretty straightforward stuff. Let's say that a person buys a palladium ring, and that ring has a mass of 5.17 grams, and it displaces 0.430 cubic centimeters of water. We want to know if the ring's genuine. The literature value for the density of palladium is 12.01 grams per cubic centimeter. What is some information that we're given? We're given the mass of 5.17 grams. What else were we given? We were given a density value. What else were we given? The volume that it displaces. So 0.430 cubic centimeters. So this displaces means that it moved that amount of water out of the way. Displacement, which we'll be doing a little bit of today, I think, or Thursday, depending when your lab is, that's a way of measuring irregularly shaped objects, things like rings or blobs of metal, because you can't like put a ruler on them and do geometry nicely, at least, to get their volume. So that displaces is indicating that this is our volume. Cubic centimeters is also a unit of volume. So we can do what with that? We can calculate density, that's exactly right. So we're going to take our 5.17 grams. We're going to divide by our 0.430 cubic centimeters. What units are we going to get out? Yeah, grams over centimeters raised to the third power cubic centimeters. And how many significant figures do each of our numbers have? How many do we have for this 5.17? 3 sig figs. And how about for the bottom number? Also 3. That 0 at the front is a leading 0. Leading zeros are never significant. Okay, so we plug it into our calculator. Thank you, calculator. 5.17 divided by 0.43. And we get out a big number, or a long number at least, 12.023255581. Yes, I expect you to write the whole thing. And we're rounding for 3 significant figures. So we're looking at the first 0, and the 2 to see how we round. 2 is smaller than 5, so we're going to truncate. 12.0 grams per cubic centimeter. Is that our final answer? What was the question? Is the ring genuine? So this is not our final answer. Our final answer is, do we think it's genuine? We got a value of 12 grams per cubic centimeter. The density is 12.01 grams per cubic centimeter. That's about as close as you can get. So I would say that yes, it's probably, almost definitely, genuine. If we were really sus about it, then we might do some other tests, or we might take it to a jeweler and have them run some other tests on it to, figure out its properties. But yeah, probably a genuine ring. And we will pick up on this slide density conversion factor next class.